I don't know how that happened. Welcome to Stochastic Control. As we noted, there's 3 parts to this course: Markov models, optimal control, simulation, and learning. And I was talking about autonomous cars as being one famous example. Google became famous because of chess. Now, none of us care about chess. But chess is an example of a game which is outside of the scope of this course. There'll be no game theory in the course. But one solution strategy to games is solving optimal control problems sequentially. So basically, you solve your optimization problem given my strategy, then I solve an optimal control problem given your strategy, and we repeat that. And that's how Google solved the chess problem. But they did it using reinforcement learning techniques, which if you wanted me to, I could explain to you in 1 hour. I mean, right now. It's so simple, it's ridiculous. So you will know how to program a computer to learn how to play chess is better than any human. And if you have access to a $1 billion computer, then after 47 days, you'll have an algorithm that works. I mean, this is a massively complex problem. And so that's the other reason this has grown, is that when I started out, I think back to when my first paper in reinforcement learning was in the 90s. And my computer, I don't know. I think memory was measured in kilobytes or something. It was getting to megabytes or something. I don't know. I mean, it's ridiculously slow. It was worthless. And so it's so exciting now to come up with a crazy idea and try it out. But okay, so we'll go through this. And I just want to warn you, and I'll warn you again and again and again, that this is an immature science. Reinforcement learning basically doesn't exist. There's a bunch of hacks and ideas, and they're all crappy. and I know we'll do better. There'll be completely new ideas, but I'm going to teach it to you anyway, because it's sort of like these are things that people use today, and you understand those really well. You'll see the problems with them, and many of you are going to go off and do research and come up with much better ideas. Right? All right, and this is going to be fun. So this has been a blast every year. And so another thing I want to say is that I'm going to do my best to try to sneak this stuff in early and have you play games and do simulations right away, like starting next week. So you don't have to wait till the end to get to play around. So it's a very foundational course. I mean, it's very linear the way it's presented here. I'm going to try to mix it up. And I say that every year. This year I'm going to do it. Right, Joel? I'm going to do it. Okay. So Markov models, that sounds pretty scary. So you remember, I hope you've all seen this before. You've got a stochastic process. Remember that? So this is why people run out after the first lecture. So stochastic process. We'll do it in discrete time. And x of t could be, the configuration on the chessboard. It could be, all of the data observed, for an autonomous car. All the visual images, and so forth, and also the position of the car, its speed, all that stuff. So that's the thing. This is this massively complex state space in all of these applications that people talk about today. And the notation we'll use is x of t is in some grand state space x, which is all these variables piled up together. Again, picture from the camera, orientation of the car, its speed, the slope of the hill, all that stuff. X is just a big list of attributes. And it's Markov. If I look at the probability that at time t plus 1, I'm in some set A, given everything in the past, then I can ignore all the previous information. And this is true for every A in subset of X. Now, why do I put that in quotation marks, everybody? So take a look at the handout carefully, and it'll say review. So you're going to have to review this basic stochastic processes stuff. And if you've never seen that before, then we better talk. Because basically in noise, in the stochastic methods of noise 1 and 2, you talk about just the basic, how do you define a probability? What does this mean? I know, so you haven't seen that, so we have to talk. I think you can get away with it, but I find that students who haven't ever been exposed to abstract probability really have trouble with this course. Luckily in the course, typically we can just say A is open or closed. Say. We put some restrictions. But I don't know. You'll just have more trouble with this course if you haven't never seen. If all you've seen is like the combinatorial probability, then you'll have trouble with the course. All right, so that's the Markov property. Excuse me. And it has. We have. And typically we assume stationary increments. We always will. So that given my current, oh wait. Sorry. All right. So a conditional probability is just some function of the observation. In this case, the observation is a state at time t. So for some given x, at some time t, I observe. X of t equals x. I observe that I'm going 45 miles an hour in that direction, and I see the beautiful blue sky and all of that. All right, that's x. It's a current configuration. Then that would be the same as if at time 0 I observed x and want to know the probability in A. All right, and so this is what we're going to assume throughout. It's just it's a compact class of models which is good enough. So no system is Markov. There's no such thing. Just like no system is linear. All right? There's no such thing as a linear system. Give me an example in nature of a linear system. There's no such thing. And there's no such thing as a Markov chain. And there's no such thing as a Markov chain with stationary increments. These are models. Okay? And this is the model we're going to take throughout the course. All right. All right. So, and again, we'll typically take, again, X is typically a subset. Yeah. N big, in part 3 of the course, the motivation is that we're in high dimensions. And so it's impossible to compute anything. Okay. All right. But let me give you some simple examples. The simplest example is a linear state space model, okay, where you just have what's the notation I'm using? Yeah, so sorry, here I'm using A for a set, and here I'm using A for a matrix. That's life, okay? Okay, so there is a linear state space model where this is what would be called a disturbance in a linear systems course. Okay? It's a disturbance because x of t is the reality, you know, it's the chessboard or the air around a car. And it's really affecting the system, unlike measurement noise, you know, which is some artifact of our bad sensors, okay? So that's a disturbance. All right, and what assumptions do you have to make on n to get the Markov property? Oh. Okay, so basically I want, given everything about the past, I don't need all that information. I only need the last guy. Yeah. You see, I mean, just think about it. The probability that x of t plus 1 is in some set S, and I wish I'd used S over there, given that x of t equals x, well, that's equal to the probability that so this is easy. Well, actually, that's true. Okay. And so that's a fact. And so we can write down this transition probability. And so first of all, what do we need for stationary increments?
X0.
Oh, no. I mean, how do we make sure this doesn't depend on time? That's all. Right? What's that? Identically distributed. Okay, so that's called identically distributed. All right, so that's just part of the story. So we know to get stationary increments, we're going to have identically distributed of t. All right, but in order for this, plus. In order for this to not depend on the previous observations, right? Then there can't be any value in collecting this information, all right? And that means that this has to be totally new. You know, it means that but based on previous observations, we can't predict this new noise. So this new noise has to be independent of the past. And if n of t plus 1 is independent of the past, now we know that n of t is IID, independent and identically distributed. Okay, I'm just going to write down the symbol, IID, independent and identically distributed. And that's the assumption you make. All right, and that's what you get to get the Markov property. So we'll talk more about this later. So why did I assume a linear model? No reason. There's absolutely no reason at all. Okay, so if you take, it's like example 2. That is a Markov chain, and it basically is the only Markov chain. So if somebody says, I've got a Markov chain, and they describe it to you in some way, you'll tell them, I will find you an F and an ID process N, so for which this equation holds. So this is every Markov chain with station increments is of this form. You know, I mean, and the construction isn't that big a deal. I'm not going to do it, but it's a fact. So saying this, and this is the same as saying that for some F. You know? And so F, F is some function. It takes some noise. I'm not going to tell you what the noise is given this. It's just an ID sequence. And F is some function, and you'll get consistency if you do it. Now this is what you typically start with. Basically, you've got Newton's laws, you've got other kinds of laws, and you pump them all in, and you get a model. and then you have some distribution of n, which typically you don't know very well. Right? I mean, basically, maybe you'll assume it's Gaussian like you did there. I mean, no, we didn't do it there, did we? So it's typically assumed that a typical assumption is that NT it's typically some noise is Gaussian for computation. Not that we believe any noise is Gaussian, except maybe communications people do. They actually, they're not even calm. Okay, not even in calm. But you do it for computation, and it's often a reasonable approximation in some applications. But there's a Markov chain, and let's write down its transition matrix, or probability. And again, I wish I'd used S here. So let's work this out. So this is called the transition probability. Actually, it's called the transition kernel. Let's just put in the notation, the language. This object. So there's a function P, which is a function of the state and set, some class of sets. Say all open sets. I'm not going to talk about measurability yet. And it is this transition probability that we introduced here. And what is everybody? Write it down before I do. So I'm told that x of t equals x, and this guy is an independent, identically distributed sequence. So first of all, you can just substitute, right? You all doing that? Okay, cool. Okay. And then that's not A, that's S now. So S is just some set. Give me a set, I'll compute a probability. Just like given where I am now, I want to compute the probability of transition. And the independence assumption is what allows us to just plug in and be done. I mean, you can take the one more step if you want. All right, this is equal to this because you know x of t is x, you could just plug in. But the fact that this is independent, identically distributed means that, and x of t is just a function of the past noise, or disturbance, this x of t is independent of nt plus 1. And so knowing x of t doesn't tell you anything about nt plus 1, and that's why you get, just like we did there, and if you wanted to, you could write this out, like if this could be some integral. Let's get rid of this. I know. So I'm doing. So if n has a density, if the distribution has a density, and then this is the indicator function. So it's a logical expression. So it's 1 if this is true, and 0 else. All right. So if this again, I didn't say where it was. Let's assume it's equal to Rn for now. It doesn't have to be. It could be a subset of Rn. But so f maps x and n to x again to a Rn. And so if this vector in Rn lies in the set S, we get a 1. Otherwise, it's 0. Right? So we could compute this, but you never will. Nobody ever will, and because it's too complicated. And why would you want to? So why on earth do we care about any of this? So far, I'm hopefully reviewing what the Markov property is and giving examples. But this little object here is the foundation of everything in this course. Okay? It is the foundation of reinforcement learning, every single aspect. Reinforcement learning is about, this is a seed of every little algorithm that you'll find. Okay? And so there's lots of motivation to really understand this well. Okay. What else do I want to say? So what do we do with it? So again, this is typically going to be something in closed loop. But, we basically put a control system in our car. It's running along, and we want to see if it crashes into a tree in 15 minutes or if it actually survives for a while. So we're going to want to watch this thing evolve in time. I haven't given any examples that aren't sort of finite time control problems. I mentioned the autonomous car, where you just want to drive across a city and stop. I mentioned chess, where you play until you win. But they're, in flight control and just cruise controls in automobiles and so forth. In finance, you want to run the thing forever and make as much money or do as well as you can. And in those cases, you want to talk about some sort of regularity in the system. So, and that's when this question comes up. Is some sort of like stability. Now, how you define stability is really subtle. And one way people, sometimes they equate it with the existence of a steady state. and a bit more. Keep it as S. So you look at the given any initial condition, you look at the probability that I'm in some set S at time t, and you look at large t, and you presume that that's equal to some function of S independent of x. And pi is called the invariant probability measure. All right, so that's sort of why do you do this? Because it's simpler. You know, that's part of it. And it's nice having just one little object, this one little invariant measure, which you can just think about. Forget about all these probabilities and blah, blah, blah. Just think about the long range. And we will see it's not true that in the long run we're all dead. It turns out that in control, if you think about the steady state, you actually deal with transients as well. Now that's a beautiful fact that I'm going to exploit a lot in this course. And I'll explain that as, I mean, how much time, we don't have much time, do we? But I was hoping to actually give you a hint of this. Maybe we'll have to wait till next time. So I'm introducing a bunch of notation. Don't be scared. There's a bunch of notation. We're going to review this again and use it and use it and use it. This is probably notation you never saw before. It's a way to not have to worry about whether I'm talking about density. It's discrete. This could be a finite state space Markov chain, you know. And then I just mean p of. Then this integral is a sum, and I'm summing over all possible x's. C of x times the probability of x. It could be this is a density. It could be a mixture. It's really convenient just to be able to write this down, okay? So this is just equal to the expectation of C of x when x has distribution pi. All right. All right. Now, I'm talking about a cost function, and in a control context, I want to minimize this. That's because my background is control. If I was in finance or operations research, then I would have a reward function. I'd want to max